Hi everyone, I am Shashant Randava and I'm excited to welcome you to my project on predicting channel attenuation models for hybrid RF FSO systems using machine learning. Since the invention of early communication systems like smoke signals, drums, and beacons, communication technologies have advanced significantly to become the high speed digital networks that we use today. However, the impact of weather on communication systems has remained constant throughout time. For example, rain and high humidity can greatly diminish the efficiency of smoke signals. Similarly, raindrops absorb and deflect radio waves, increasing signal loss, which impacts the overall communication quality. These challenges have persisted as we transition from ancient method to modern day communication technologies. In this project, we focus on addressing the challenges of reliable communication in outdoor environments, which are often influenced by varying weather conditions. Hybrid radio frequency and free space orbital systems are promising solutions to enhance communication performance by leveraging both RF and FSO channels, offering diversity gain and improved robustness in adverse weather scenarios. The core of the project involves the creation of generic random forest models which are adaptable across different weather conditions and maintain the correlation between RF and FSO attenuations. Through testing on empirical data, we demonstrate that these machine learning models outperform traditional ITUs models and linear regression based models in terms of accuracy and error metrics. Before going deeper into the project, let's first define the key technologies involved. The term radio frequency communication describes the use of electromagnetic waves in the radio frequency spectrum, usually between 3 kHz and 300 GHz, to transmit data or signals. Radios, TVs, mobile phones, Wi Fi networks, and satellite communication are examples of wireless communication devices that frequently employs radio frequency waves. Free space optical communication is a system that sends data wirelessly across the atmosphere using light, usually in the visible or infrared range. When transmitting data between two sites, FSO employs highly concentrated light beams such as laser as opposed to radio waves, which are utilized in RF communication. Moving on to our empirical data. The dataset includes 22 weather parameters, which serve as the predictor variables. These parameters include absolute humidity along with its maximum and minimum values, which indicates the moisture content in the air. Additionally, distance measures the separation between the communication points, and frequency represents the oscillation rate of the signal. The dataset also includes particulate levels along with the maximum and minimum concentration, which provides information on airborne particles. We also have rain intensity, including its maximum and minimum value, to capture the varying rainfall levels. Relative humidity gives the percentage of moisture in the air, while the sign-up code provides a standardized description of the weather conditions. Temperature, along with its maximum and minimum values, reflects the daily temperature range, and time indicates when the data was recorded. The visibility parameter, along with its maximum and minimum values, measure how far objects can be seen, while wind direction and wind speed, including their maximum and minimum values, capture wind-related data. The target variable for an analysis are FSO attenuation and RF attenuation. These predictor variables helps us analyze and predict the RF and FSO channels attenuation under different weather scenarios. In our dataset, the sign-up code is used to clarify different weather conditions, with each code representing a specific type of weather. The code 0 corresponds to clear weather, 6 indicates rain, 5 stands for drizzle, 8 represents showers, 4 refers to fog, 7 indicates snow, and 3 denotes a dust storm. In our dataset, we have around 57,000 records for clear weather, 25,000 for rain weather, 6,000 for drizzle, 1,700 for showers, 500 for fog, and around 400 for snow, and only 190 for dust storm. To analyze the data effectively, we will be dividing the dataset based on these sign-up codes, allowing us to examine the impact of specific weather condition on RF and FSO attenuation. Each subset of the data will be treating according to the respective weather scenario, enabling a more accurate prediction of channel attenuation. With that out of the way, let's talk about the correlation matrix. This heat map gives us a clear picture of how different environmental factors relate to each other. The color gradient makes it easy to spot strong positive correlation as shown as by deep red color and strong negative correlation shown by deep blue color. Now, looking at the smaller correlation map, we can see that some features have perfect correlation of 1, particulate, maximum particulate and minimum particulate, rain intensity, maximum rain intensity and minimum rain intensity, temperature, maximum temperature and minimum temperature, visibility, maximum visibility and minimum visibility, absolute humidity, and maximum absolute humidity and minimum as well. Since each set of three variables said above is perfectly correlated, they essentially carry the same information. Keeping all three in the dataset would be redundant, leading to multi-collinearity, which can mess with machine learning models and inflate variance in regression analysis. To simplify things, we can remove two from each trio to keep just one representative variable, which we will deal while doing feature importance later. In our next step, we start with basic machine learning models, that is linear regression, k-nearest neighbor, support vector machine, and decision tree, to understand how the data behaves and how well these data can predict FSO attenuation and RFL attenuation. By testing different models, we gain insights into the relationship within the dataset and how various algorithms respond to it. The process begins by iterating through multiple data sets, cleaning missing values in the target column, and splitting the data into feature and targets. To ensure consistency, the features are scaled before the dataset is divided into 70% training data and 30% test data for evaluation. Each model is trained on the training data and then tested on unseen data to assess its predictive performance. We use root mean square error to measure prediction accuracy and R2 score to determine how well the model explains the data variance. After running the previous function and getting the result, we decided to plot the result as bar chart to compare the performance of different models. The top two charts shows root mean square error for FSO attenuation and RFL attenuation, where lower values indicates better prediction. Decision tree and SVM generally have lower RMSE value compared to linear regression, which struggles especially under conditions like drizzle and fog. The bottom two charts display R2 scores, meaning how well each model explains variance in the data. Higher R-square values indicate better performance, with decision tree consistently achieving the highest score, often above 0.90 across most weather conditions. These visualizations confirm that decision tree is the most reliable network, delivering both high accuracy and low error. Also, these results tells us a lot about the nature of the data and how different machine learning models interact with it. Decision tree performing the best shows that the data is likely nonlinear and involve complex interaction between features, whereas linear regression struggles since there is no linear relationship in the data. Since decision tree already showed the best performance in our previous result, choosing random forest regressor is the next logical step. Random forest enhances the strength of decision tree while addressing their primary limitation, overfitting. A single decision tree tends to memorize patterns in the training data, which can lead to poor generalization on new data. Random forest mitigates this by creating multiple trees, each trained on random subset of the data and features. Given that a data likely contains nonlinear relationship and complex dependencies, random forest's ability to capture integrate patterns while avoiding overfitting makes it the ideal choice. It retains the flexibility of decision tree but adds better generalization and predictive accuracy. We will also use OOB out of bag to help us understand feature importance. OOB will work by training the random forest on a subset of data and then using the remaining data to estimate how well the model would perform if certain features were removed. By monitoring how performance changes when one feature at a time is removed, we can gauge the importance of each feature in the model prediction. After applying the previous algorithm to the dataset containing sign-up code 0, which stands for clear weather, we analyze the out-of-bag scores. Based on these scores, the 7 predictors that can be removed are sign-up code, temperature, temperature difference, maximum temperature and minimum temperature, time, and visibility. These features exhibit minimal impact on model performance when removed, as indicated by their relatively small increase in RMSE score and stable R-square values. This suggests that their contribution to the predictive power of the model is either redundant or already captured by other features. In real life, factors like temperature and temperature-related variables do not have a significant impact on RFL and FL and FSO performances. FSO communication relies heavily on atmospheric conditions such as humidity. Similarly, time also does not have effect on FSO and RFL communications, as we can see by these OOB scores. The OOB scores for sign-up code range shows that the seven predictors that can be removed are sign-up code, rain, temperature, temperature difference, temperature maximum and minimum temperature, time and visibility. These features exhibit minimal impact on model performance when removed. The temperature-related variables do not significantly alter the model performance, meaning they may provide overlapping information. Similarly, rain does not appear to be a critical factor in the prediction. While rainfall can affect FSO and RFL in real life, it seems that other features in the model are already capturing its impact, making it the variable redundant. Time and visibility also show little effect on RMSE and R-square, indicating they are not strong predictors. Same can be said for the data set containing sign-up code result, as the seven predictors that can be removed are sign-up code, temperature, time, and visibility. These features exhibit minimal impact on model performance when removed, as the RMSE values remain relatively stable and the R-square values do not show a significant drop. This suggests that their contribution are either redundant or captured by other features. For sign-up code shower, from the graph we can see that removing important features such as frequency, rain intensity, and humidity greatly increase the RMSE square and reduces the R2 square, further showing that these are the important predictors, whereas features such as temperature and temperature difference, time, visibility does not hold much importance to these showers. These patterns also hold for sign-up code fog and sign-up code snow, as there is no massive spike in the scores of RMSE and R2 when the features are removed. The model performance remains stable, indicating that their influence is either minimal or already reflected in other variables. Removing these features will simplify the model while maintaining performance, improving efficiency, and reducing the risk of overfitting. For the sign-up code dust storm, we can see that features such as visibility, time, and temperature related have relatively low R-square values, below 0.90, indicating they have contributed less to the model performance. Additionally, for both models, wind direction and related to wind also show weaker R-square values, particularly in the FSO model, where some are below 0.75. Since these features have fewer records, their removal causes the scores to spike, but this does not necessarily indicate strong predictive power. These features can be removed without significantly compromising the model's performance, allowing the model to focus more on informative variables that have higher explanatory power. The following graph compares the root mean square error values for two different modeling approaches, a generic model and a specific model. The generic model refers to a single random forest model trained on the entire dataset, while the specific model consists of separate random forest models, each trained individually for different sign-up codes. From the graph, it is evident that FSO RMSE experiences a significant peak in RMSE during the storm for the specific model, suggesting that the specific model struggled more in this condition. This could be due to the limited amount of dust storm data available for individual sign-up code, leading to poor generalization. In contrast, the generic model, which is trained on the larger, more diverse data set across multiple sign-up codes, can leverage information from other stations and might perform better in scenarios where certain weather conditions have limited data. The next graph compares the R2 score for both modeling approaches, the generic and the specific ones. It is observed that the RFL R square for generic model consistently achieves high scores, while the FSO R square has lower values clearly for clear wind drizzle, suggesting that the specific model may struggle under certain conditions. The RFL R square for specific model shows fluctuation, performing well in some conditions, like fog, but dropping significantly in showers, thus leading to the important observation that due to having a limited data for specific sign-up code, the generic model perform better as it is trained on more data set. This project aims to evaluate different modeling approaches using empirical data, demonstrating that nonlinear models based on the random forest algorithm significantly outperform linear regression models with interaction terms. To further enhance model performance, hyperparameter optimization will be conducted in future work. Additionally, a heat map visualization will be utilized for comprehensive comparison of the models, offering deeper insight into their predictive effectiveness across various weather conditions. Thank you all for your time and attention.